never know how long it's going to take me to get my cursor where it belongs, so thought I'd get started. We'll give Leo another minute or two, but he's often on the road at this time, so he may or may not be available.
So John, why don't you go ahead and take it? And I think we'll have one more student joining us, but he's sometimes late.
There we go. The mute button was hiding on me. Presumably I can now be heard.
Yes,
or not.
you can.
Yes, okay, very good. And everyone is seeing the introductory slide, I assume, as well. All right, well, today's topic is antennas. And when you start talking to hams about their shacks, the subject of antennas always comes up because antennas are probably the most critical part of a ham radio station. Doesn't matter how fancy your transceiver is or what other equipment you have. If you don't have a good antenna, you don't have anything. And that's not really exaggeration. So the topics on antennas and feed lines for the exam broken down to a bunch of subtopics that are listed here. We're going to cover them and not necessarily in this order, but there's a bunch of subtopics, as you can see here. And we're going to delve right into first talking about some definitions up front, terms you're going to be seeing throughout this. What is an antenna? Well, it's what facilitates sending the signal out to some distant station. A feed line connects your station, your radio, to the antenna. We talk about test and matching equipment. These are pieces of equipment that allow you to monitor antenna performance or adjust antenna performance. The feed point is where the transmitted energy enters the antenna. It's where the feed line connects to the antenna. We'll talk about that. An element is a conducting part or parts, could be more than one, of an antenna, and that's what's designed to radiate or to receive the radio waves. A driven element is the element that's supplied directly with power from the transmitter. And when we talk about directional antennas, we'll get more into this. Polarization is the direction of the electric field remember that the radio waves are composed of an electric field and a magnetic field. And then they're at 90 degrees to each other. The electric field, the direction of that electric field relative to the surface of the Earth. And it will be the same as the physical direction. So if you have a vertical antenna, you will have vertical polarization. If you have horizontal antenna, you will have horizontal polarization. Or if you have an antenna on a funny angle, you'll have weird polarization. But that's what we're talking about when we talk about polarization. So let's talk a little bit more about that, vertical and horizontal polarization, and we'll talk about the pattern that a dipole antenna, an illustration of where the energy comes out of a dipole antenna and what that shape that takes. So as I already mentioned here, we talk about horizontal and vertical. There's a number of ways that you can classify antennas. You can talk about their orientation, horizontal, vertical, so forth. But you can also talk about size and shape. We can classify them by an operational parameters such as gain, which we'll be talking about, directivity or impedance. We can also arrange them by physical properties, like are they flexible, are they shortened, are they loaded, are they active? There's lots of different ways to classify antennas. For exam purposes, there's 3 things that we actually care about, and that's what's on the slide here. We care about orientation, directivity, and size. Okay, and by size, we're talking about in relation primarily to the wavelength of the signal that's going to be transmitted or received. On directivity, we're either talking about something that's omnidirectional in all directions, or it has a focus in a particular direction. So these are the 3 things we're going to be interested in. So this is an illustration of basically a half wavelength dipole antenna. You can see we have an open wire that feeds it in the middle there. The things that sort of look like they got loops around them with some eyes on either end, those are insulators. So you can see how you've got basically half the antenna on one side and the other half on the other. It's a half wavelength overall, which means each side's a quarter wavelength. And remember, the formula for wavelength is 300 in meters. Wavelength in meters is 300 divided by the frequency in megahertz. So a half wave dipole overall length in inches would be the wavelength divided by 2 times 39. Divided by 2 is a half wavelength, and 39 is a conversion factor from meters to inches. Now, the actual physical length of an antenna is going to be slightly smaller because electron flow through a conductor is slower than the speed of light. There's resistance in the conductor. This decrease in speed is referred to as a velocity factor, and it's usually expressed as a percentage. So, for example, we say that copper has a velocity factor of about 95% of the speed of light. So that also means that an antenna made of copper will be about 95% the size of the theoretical value that you get with this formula. So your actual length you want for your antenna will be slightly less than this theoretical length. This is a radiation pattern for a half-wave dipole. As we just saw, a dipole's half wavelength, a piece of wire connected to the center, quarter wavelength on each side. The red line through the middle there, assume that is the dipole, and you can see that there's lobes above and below showing a radiation pattern. This would be sort of an ideal one if it's a half wavelength above the ground, so it's not getting interference from the ground. If you were to look at it from the end, it would look like a donut around there. As you lower the antenna closer to the earth, it's going to, the lobes get flattened until it becomes essentially omnidirectional. All right. So vertical antennas. So this is an example of quarter wave vertical antennas. Again, the physical length is going to be slightly smaller because of the electron flow through the conductor. And you can see here it shows that there's a quarter wavelength above. The other quarter wavelength is what's called your ground plane. That could be literally the ground on the right. It could be radials that are sticking out in various directions, or the mag mount antenna that you put on the roof of a vehicle. The ground plane would be the metal of the vehicle's roof. So coming up with your length of the actual radiating element there that you can see, the quarter wave is going to be the wavelength divided by 4 instead of 2 now, because it's a quarter wavelength, times the conversion factor of meters to inches of 39. This is the kind of radiation pattern you can expect to get from a quarter wave vertical antenna. And you can see that it's not a lot of energy going up. It's mostly going out to the side, close to the ground. And that can be very good depending on what you're trying to do, but that's usually what you want with your vertical antennas. The your standard quarter wave vertical has, as it says here, has a typical feed point impedance of about 35 ohms. You're going to be feeding it through a 50 ohm line, so that's a mismatch. But radials, by adjusting the direction of the radials, you can adjust the impedance. So if you slope them down, it raises the feed point impedance. All right, so let's take a look at some exam questions that relate to these topics. Which of the following describes a simple dipole oriented parallel to the Earth's surface? Well, if it's parallel to the Earth's surface, that's what we call horizontal, right? So it would be a horizontally polarized antenna. In which direction does a half-wave dipole antenna radiate the strongest signal? You think back to that diagram we had, and we talked about looking at it on end. It would look like a donut. If you're looking at it from the side, which direction does it go? It goes broadside to the antenna. Doesn't come off the ends. It's broadside to the antenna. Now we're going to talk a little about some other concepts here. Antenna gain is an important one. We'll talk about beam antennas, a little bit about loaded antennas, and portable and mobile antennas. So basically, this is an area where bigger is better. The larger percentage of a wavelength that the antenna is, so half would be better than a quarter, 5/8 better than a half. For vertical antenna lengths, bigger is better, so to speak. And you can see here it's illustrated by this pattern looking elevation. So you're looking at an antenna sticking up, pointing up towards the top of the page in the center there. And you can see that the pattern of the radiation going out, the quarter wavelength antenna is the two big loops on each, one on each side. You can see the 5/8 inch wavelength has two loops on each side, and one of them is pointed down more. So there's more energy going out horizontally along the ground. So if you want to talk to somebody else on the ground, you're getting more energy in their direction. That's why a 5/8 would be even better than a half or a quarter. Beam antennas. When we talk about gain, we're not talking about actually adding any power. You only have so much power coming out of your transmitter. You can't add to that. You can't increase it. There's no way to make more energy, because you only have a certain amount of power coming out. But what you can do is focus that power in a particular direction, which is what beam antennas do. You can think about this like a balloon. So you've got a balloon full of air. It's nice and round. If you squeeze it in on the sides, it's going to pop out in another direction. That energy, in the balloon's case, that air has to go in one direction. So if you squeeze it down in one area, it's going to get bigger in the other area. And that's kind of what we're doing with the energy. So this is an example of a beam antenna, a Yagi antenna, named after Dr. Yagi, a scientist from back in the 20s or 30s who invented this. And you can see this is your basic sort of 3-element Yagi antenna. In the middle, you see a feed line comes in to one element, which is called the driven element. To the left of that is another element called a reflector, which basically acts like a mirror, reflecting the signal in the opposite direction towards the right. A director is another element. You can have one or more of the directors in the direction that you want the energy to be focused. And you can think of it as acting like a lens. If you think about this like light, you've got a mirror bouncing the light back and a lens focusing it so it gets brighter in one direction. Well, it's the same concept we're doing here. Directors and reflectors are referred to as parasitic elements because they're not actually being driven by the feed line. They're just, again, either reflecting the energy or focusing it forward. Reflectors are about 3% long. And this is what it looks like to be looking from the top of a Yagi antenna. And you can see the energy pattern. It's strongest at the top there. And there's basically a null. There's nothing sort of on the sides at 90 and 270 degrees. It basically goes down to essentially almost zero. There's a little bit of energy towards the back, but it's mostly focused towards the front, which is what we want. I'm going to throw out a term here, an isotropic resonator. This is an imaginary, a theoretical type of antenna, which would be like an imaginary point out in space that radiates energy equally in all directions. This is theoretical. Nothing like this actually exists. Manufacturers will often compare their antenna when they'll say we have an antenna that's a 6 dB gain antenna. You got to watch what they're talking about. If they're talking about in relation to a isotropic antenna, well, that doesn't even exist, and it's essentially, if it did exist, it would be a poor performer. So they obviously want to compare it to the thing that's going to make them look the best. So they would compare it to a DBI. You also see the dBd, decibels, related to a dipole antenna, in which case, what they're saying is that that's in relation to what an actual dipole is. So the difference is about 2.15 dB. So if they give it in dBi, you're going to want to subtract 2.15 from whatever number they tell you to get what it really means, which is going to be a smaller number in relation to a dipole. If somebody tells you, if they advertise that it's a gain and they say it's dBd gain, then you know they're being really honest with you. So buyer beware. Okay, so this is what a Yagi would look like, sort of superimposing a picture of a Yagi over that pattern. So that's, you can see the driven elements are out front. That's where all the energy goes. The reflectors in the back, and you have a driven element in right there between the 90 to 270 degree. This is another type of directional antenna called a quad, and again, it has a driven element, and then it has a reflector. In this case, doesn't have directors, just has the driven element and a reflector. Another term is loaded antennas. The rubber duck antenna, the thing you get when you buy an HT that comes with it, the little short stubby thing, is an example of a loaded antenna. Basically, the antenna is wound into a coil inside that rubber tubing that you see. There's actually wire inside there that's the antenna, and it's wound into a coil so that it's physically shorter but electrically longer. That's a loaded antenna. Another example is what's sometimes called screwdriver antennas, which are they use a motor and a coil inside it with a contact that moves up and down the coil to change the impedance of it. So those are loaded antennas. So let's take a look at the questions here that are relevant to this. So what is antenna gain? Well, first one, additional power added. Remember, you cannot add power, so that can't be right. It's not additional power that's required in the antenna when transmitting on a higher frequency. No, it's the increase in signal strength in a specified direction compared to a reference antenna. That would be correct. It has, and then it's not, gain has nothing to do with the impedance directly. So it's the increase in the signal strength in a specified direction compared to a reference antenna. important concept. So what is a beam antenna? I like the answer 2, named after somebody named Clarence Beam. Well, I'd prefer Jim Beam, but that's not the correct answer. It's C, it's an antenna that concentrates signals in one direction, right? That's what we've been talking about. Which of the following types of antenna offers the greatest gain? Well, we did talk about a 5/8 wave vertical having better gain than a quarter wave or a half wave, but it's not a directional antenna. The isotropic is a theoretical antenna. We haven't talked about J-poles. They don't really factor into this question. It's a Yagi. It's the one we were talking about, the directional antenna with the driven element, the reflector, and one or more directors. That's a Yagi, and it's a directional, offers the greatest gain. What is the advantage of a 5/8" wavelength antenna for VHF or UHF mobile service? Okay, has more gain than a quarter wavelength, radiates at a very high angle, eliminates distortion, or has 10 times the power. Well, no power gets increased. It may be gain, not power. And remember, it's a low angle, so that eliminates that. It has more gain than a quarter wavelength antenna. Remember, bigger is better. Which of the following describes a type of antenna loading? Okay. Well, that's going to be A, electrically lengthening. Remember I talked about the rubber duck? We're electrically lengthening it by inserting an inductor. Well, an inductor is a coil of wires. So this coiling acts like an inductor. So that would be a type of antenna loading. Which of the following increases the resonant frequency of a dipole antenna? Well, this one's might be a little confusing here. You want to increase the frequency, right? Well, higher frequency would be lower wavelength, right? Shorter wavelength. So what are you going to do? You're going to shorten it. Remember, they're inversely related. What's the approximate length in inches of a quarter wavelength vertical antenna for 146 megahertz? I know there's math here, but it's actually quite simple. Let's take a look at this. So remember the formula, 300 divided by the frequency in megahertz will give you the wavelength in meters. So if we take 300 divided by 146, we come up with 2.05, pretty close to 2, right? That's a frequency in the 2 meter band. We divide that by 4 and multiply by 39 inches, and you get 20 inches. Another way to look at this is 146 megahertz is on the 2 meter band. Half of 2 meters is a half a meter. A meter is 39 inches. So that is 19 and a half. And again, remember, theoretical length, but there's that velocity factor. It's going to be a little bit shorter. So the reality is about 19 and a half inches is about right. And that would be the answer. So same kind of problem here, slightly different numbers. What's the approximate length in inches of a half wavelength 6 meter dipole antenna? Okay. Well, we do the same thing here. So we know that 300 divided by the frequency, 6 meter, right? It's 50 megahertz is a 6 meter wavelength. So 6 meter divided by 2, because this is a half wave, not a quarter wave, times the 39 inches gives you 117 inches. And coincidentally, since we used exactly the 6 meter, the other way of doing it comes out the same. So it is going to be about 117 inches, a little bit shorter, right? So that means the only choice that's close to that is 112. It's a little bit less, but that is the right answer. Remember, it says approximate length. So was a disadvantage of the short, flexible antenna supplied with most handheld radio transceivers compared to a full-size quarter wave antenna. That's your rubber duck, right? Well, it's not mechanically fragile. It's actually pretty good. You can bend it all over the place. It's vertically polarized. It's not circularly polarized. So the only one that fits is it has low efficiency because it is not a full-size antenna, right? Bigger is better. What's the disadvantage of using a handheld VHF transceiver with a flexible antenna inside a vehicle? Well, we didn't really talk about this, but if you're sitting inside a vehicle, presumably a metal vehicle, you have a big cage around you, which acts like what's called a Faraday cage, and it shields you. So if you're inside trying to get your signal out of this metal box, it's going to reduce that strength. So a signal strength is going to be reduced to the shielding effect of a vehicle. Your HT inside a vehicle may not work, but if you have a mag mount antenna on the roof and connect your HT to that, it'll work great. Because you eliminate that shielding effect because the antenna is outside the vehicle. Okay. Moving on to feed lines, SWR, and antenna tuners. Remember we talked about the feed line and impedance and a feed point. Amateur radio transceivers, like I mentioned before, have an output impedance of 50 ohms. So your coax and antennas should be as close as possible to that 50 ohms to ensure the maximum power transfer. Because what happens is, if there's any kind of a mismatch, there's going to be some power that gets reflected back at the point where the mismatch occurs. And it creates what are called standing waves, where the energy, if you're in a bathtub and you create some waves, when they bounce off the side of the bathtub, they're going and hit the incoming wave, they're either going to offset it or they're going to magnify it, depending on how they hit each other, right? So that's what happens with a standing wave in a feed line. We use a ratio to talk about the the power out versus the reflected power, the forward power versus the reflected power. And we look at that ratio. 1-to-1 would indicate a perfect match. It's absolutely perfect. The higher the first number is, the less perfect it is. As the SWR increases above 2-to-1, a lot of your radios will start to automatically throttle back the power because that energy has to go somewhere. It either gets expended as heat in your feed line, or it gets into your radio and damages your components. So a lot of the modern radios will offset that. Anything above 3-to-1, you got to shut that down. That's going to cause damage. So that's the consideration we have with SWR, standing wave ratio. Another thing to keep in mind is that all feed lines have a certain amount of loss, energy that's lost going through the feed line. And the loss is greater the higher the frequency. So loss increases with frequency. And the longer your feed line, the greater the loss as well. So that's another important consideration we're going to talk a little bit more about. As I said, standing waves will eventually either be radiated out somewhere or they're going to be lost as heat in the feed line. So you want to reduce your SWR. This is examples of coaxial cable and hardline. Helix is a type of hardline that it's not air core, it says dielectric instead. So you've got your center core conductor, you've got an insulation between it and the shield on the outside of coax, which is going to be your grounded side of the coax. And there's a pretty good picture there in the lower right of an actual cable, what it looks like. Here's an illustration of your standing wave. You can see that as it gets reflected back, it's going to, on the right, the far right, it either magnifies or decreases the energy as they hit each other. Kind of a cool video. Coax cable signal loss. Remember I said that as you increase the frequency, the loss gets greater. And depending on the type of cable you use and the frequencies you're operating at, this can really be a significant amount of loss. So let's take a look real quick at something. And that is, if you take a look at RG58 is the kind of thin coax that you'll typically have like with a mag mount antenna coming off your car. And then that's the second one from the left. And then on the far right's a type of coax called LMR 400, which is one you really like to use for VHF, UHF installations at a fixed location. But it's really stiff and thick and hard to work with. But you can see, let's say at the 400 megahertz, it's your UHF, your 70 centimeter band. If you look across at the RG58, you'll see that it has per 100 feet of cable, you get a loss of 11.2 dB. That's more than 90% of your loss. Whereas with LMR 400 all the way over to the right, it's less than 3 dB, so it's less. You only lose less than half. So there's a big difference in the loss between those cables. So that's a real important consideration in putting together your shack. All right, so what is standing wave ratio? What is that? Well, we've just been talking about it. It's a measure of how well a load is matched to the transmission line, 1-to-1 being a perfect match, right? That's SWR. What's the most common impedance of coaxial cables used in amateur radio? 50 ohms. That's the magic number we always remember, 50 ohms when it comes to coax. That all your coax that you use in amateur radio is 50 ohm. Not all coax is that. Television coax is 75 ohm. You don't want to use television coax in your shack. You need to buy the right kind of coax. Why is coaxial cable the most common feed line for amateur radio antenna systems? Well, it's easy to use. It's a cable with a connector on the end that you can just screw on or snap onto your radio. It's easy to work with, and you don't need to do anything special with it. You just run the cable out and connect it. So that's why it's the most common. It's not necessarily the best for certain purposes, but it is easiest to use. What is a benefit of low SWR? What did we talk about as the disadvantage of a high SWR? It's going to cause a lot of signal loss. So low SWR is going to reduce your signal loss. What happens as the frequency of a signal in coaxial cables is increased? We just looked at that chart and compared some, right? The frequency of a signal goes up, the loss also increases. More loss at higher frequencies. What can cause erratic changes in SWR? So think about this. It has to do with a mismatched impedance. So if you've got something in your feed line that's not right, something that's loose or got an issue with it, that can cause changes in your SWR. A loose connection would be a good example of that. Thunderstorms got nothing to do with it. Signals from another station have nothing to do with it, and overmodulation on your mic or whatever is not. It's the only thing that has anything to. B is the only answer that has anything to do with in feed lines. Which of the following is a source of loss in a coaxial feed line? Well, we didn't really talk about this, but if you get damage inside the cable, and water is something that will definitely do damage, it's going to cause problems. But high SWR is also loss, which we talked about. And a lot of connectors, they're just another source of loss. So all of these, this is one of the few questions it seems like in this series here that where all of the above is the right answer. What is the electrical difference between RG58 and RG213 coaxial cable? Well, you'd have to think back to the chart, which we looked at before. RG58, RG213, you can see the differences in their loss, right? So RG213 has less loss than RG58. Less loss at a given frequency. Which of the following types of feed line has the lowest loss at VHF and UHF ranges? We really haven't talked about that, but it's air insulated hardline. Hardline is better than coax as far as loss. 50 ohm flexible coax is the most common thing we use. 50 ohm or 75 ohm I mentioned, that's TV coax, and you've got a mismatch with the 50 ohm output of your radio, so that's not good. And multi-conductor unbalanced cable is not something we even talked about. So air insulated hardline. What is the major function of an antenna tuner? Okay, let's talk about that. So our concern is that we have a low SWR, as close to a perfect match between the impedance and from our transmitter, the impedance in the feed line, and the impedance at the antenna. So and I mentioned, we talked about the vertical antenna is at 35 ohm, I think was what we were showed on that slide. That doesn't match, right? So we want some way to reduce the SWR, and what your antenna tuner does is it matches the antenna system impedance to the transceiver's output impedance. So it reduces that SWR. That's what a tuner does. It's also sometimes called a coupler. Okay. RF connectors. So we've got antennas, and we got radios, and we got feed lines, and somehow you got to get them all hooked up together. And that's where RF connectors come in. There's a number of different kinds of connectors. There's more than just what's shown here, but the most common one you'll find is the PL259, which is the plug side of it, the male connector that goes into an SO239 socket. But generally people just refer to this as a PL259 or a UHF connector. It's actually not the best thing at UHF. It's better at HF. The best thing at UHF range is what's called an N-type connector, but they're more expensive. You can see the N-type is right about in the middle of the chart on the left. It looks similar to the PL259, which is the one on the far right of the right picture. It looks very similar, but it's slightly different. And you don't want to try and plug one into the other. Okay. And I just gave you the answer to this one. Which of the following RF connector types is most suitable for frequencies above 400, set at the higher UHF frequencies that you want a type N? It's better than the UHF, the PL259, SO239. The other types of connectors are for different purposes. to type in. Which of the following is true of the PL259 type coax connector? Mention that as well, that they are commonly used at HF and VHF frequencies. The higher frequency UHF, your preferred type of connector would be a N-type connector. I also see a lot of bayonet types like BNC connectors people will use because they go on and off quickly, but they're not the best type of connector to be used. And it's not what why you would use a 259, because it's not a bayonet connector, it screws on. Any questions about anything we covered today? Went through it all pretty quickly, but there's not a lot of questions on the exam. You'll get one from each of these sections, essentially. So you have 2 questions out of all of these you will get on your exam.
I don't have any questions, but thank you. Really helpful summary that you did. So really appreciate that.
Good, good. Well, I guess if there's no questions, we're actually done a little bit early, because this wasn't a big section. Like I said, you're only going to get 2 questions out of this pool, so there's not a lot of questions there. It's an important topic, but fortunately not a lot on the exam. Right. All righty, let me close out of this.
Well, I'm going to go ahead and stop the recording if this sounds like a good place to stop.
Yep. And I'll stop sharing. There we go.